Ah, kids. All right. This one is about circular motion and gravity. Couple things just to remember as far as some basic stuff you need to understand with circular motion and gravity is you need to understand the word centripetal. Remember, this means going in a circle. This means towards the center. So this is going in a circle, moving or pointing towards the center in a circle. Why is this important? Because if something is moving in a circle, the net force always points towards the center. So if the net force points towards the center, we actually give that net force a special name. We call it Fc. Okay, but again, Fc is just a special net force that causes something to move in a circle. Okay, which also means that, if you think about what we learned about before, that hey, acceleration depends on the direction of the net force. This is again how the College Board writes it. Well, that means that centripetal acceleration depends on the centripetal force, which means the centripetal acceleration has to point towards the center. So if something's moving in a circle, even at a constant speed, it's going to be accelerating towards the center. Okay. Couple other basic terms you need to know is period. Okay. The amount of time it takes to go around once. So if you understand that, the amount of time that it takes to go around once, if you are making a bunch of circles, for example, you're spinning something around and you time it, and you want to find the period, you would say, well, it would be the time divided by the number of revolutions, because it's the time that it takes to go around once. By the way, that equation's not on your formula sheet because College Board expects you to know it. Frequency, which is a lowercase f, is how frequent you complete a circle. So again, if you were doing that, it would be, well, if you're going around so many times and you time it, that would be the number of revolutions divided by the time. So if you look, hopefully you can see that f equals 1 over the period, or on your formula sheet, it's actually written like this. Period equals 1 over f. Okay, that's how it's written on your formula sheet. But that formula is on your formula sheet, so just be aware. Make sure you can locate it. Let's see. We spent the first couple days, we were doing the smorgasbord. If I have something move in a circle, let's say at this point, and it's moving around counterclockwise, that means my linear velocity is pointing that way. Okay. And it is going to be accelerating towards the center. Do you see? Remember when we went back, hey, look, if you are moving this way, but you're accelerating that way, that means that you're changing your direction. So, if you have a constant speed and moving in a circle, it's changing direction. Also, if you remember the reason that something gets stuck, if you're going around a corner real fast in your car, it feels like you get thrown to the outside. The reason that happens is inertia. Really, this unit is just an application of Newton's laws. Why do you get thrown or feel like you get stuck to the outside, or feel like you're thrown to the outside? It's just that you have inertia and you're trying to move straight, and the car is preventing you from moving straight. So inertia. And then let's see, we had this formula. If you remember, if you're going at a constant speed, then you had V equals D over T. That was a lovely equation to use if you're going at a constant speed. Well, if you're talking about a circle, the D around a circle is called the circumference. And then if you are going one time around a circle, that period, the time would be the period. So we use this equation quite a bit. And then if you remember, this was true of AC. AC is equal to V squared divided by R. And again, this formula is on your equation sheet, so I would just recommend make sure you can locate it there. So this one's not there. Again, why? Because the College Board expects you to know distance over time. So that's your basics. This unit, as I said, is essentially just Newton's laws. So, we had lots of problems where you had to draw your FBD. So, for example, let's say you had, I don't know, something that is moving around in a circle. Okay. If it is a loop-to-loop. Now, again, I'm going to go through an example. You need to treat every problem separate. Every problem is potentially different. If it's a loop-to-loop, here's what your FBD looks like. You would say, well, I have this normal force pointing down. I have this force of gravity also pointing down. At the bottom, I have the same force of gravity pointing down. But if I'm moving in a circle, I have to have a bigger normal force pointing up. Okay. Why? Because it has to be accelerating towards the center. And then after you're done, you would just use your picture, just like in our last unit, to write your equation. So this would be Fc equals Fn plus Fg. This one would be Fc equals Fn minus Fg. And then you would plug your stuff in and solve. Remember, the Fn is the normal force, but it's also called sometimes the apparent weight. If you have ever ridden in a roller coaster, you know you feel heavier on the bottom of a loop. Why do you feel heavier at the bottom of a loop? Because your normal force is bigger. Okay. The normal force can change. If a roller coaster is designed well, you can feel like you're weightless. Well, that would be because your normal force is zero. In fact, that would also be, hey, if you were to do a problem like this, let's say you're the top of a loop, and you wanted to figure out what is the minimum speed just to make it through, well, then the only force acting on you would be gravity, and you would write your equation, Fc equals Fg, and this is mv squared over r. This is going to be m times g, and my m's go away, and then I could solve. But again, you're not memorizing, you are understanding. Every problem is potentially different. If we had a problem where, hey, you have a loop, or you have a roller coaster that goes like this, or it's like the bottom of a circle, top of a circle, and it asks you to draw your FBD at the bottom, and it asks you to draw your FBD here. At the bottom, you would have, just like up here, big normal force, smaller FG, because it has to accelerate towards the center. Now your FG is the same as it was over here, but your normal force has to be smaller. Why? Because if you're going to stay on that circle, you are going to accelerate towards the center. We did problems where you had, for example, a coin on a turntable or a car that's going around a horizontal circle, and in that case, your FBD is going to look something like, let me try it again, your FBD would look something like this. So if I have a car going around a corner or a coin on a turntable, you get the normal force pointing up, you have the force of gravity pointing down, and then you would have static friction, okay, pointing that way. And then which way would this car be turning? It would have to be turning to the right. Why? Because it has to accelerate towards the center. The centripetal force always points towards the center. And then you could, solve for things. Oh, in this case, my normal force equals mg. So then my FF equals mv squared over r. So mu mg equals mv squared over r. Oh my gosh, your mass cancels out. But again, don't memorize, understand. Every problem is potentially different, okay? We did problems where we did our flying pig, where you had, this thing was like this, but it's going around in a circle like that, okay? If you draw your FBD, you have this tension force, you have force of gravity, and then you'd have to break this guy into its components. This is my tension, and then you would see this force and this force have to cancel. Hey, look, there's my FC. That's the one that's pointing towards the center, and then you could solve stuff. But again, don't memorize. Set up your equations. Draw it. It's always picture. Use your picture to write your equation, and then solve for the problem. The rest of this unit was talking about gravity. You remember the universal law of gravity was Fg equals gmm over r squared. At least that's how I like to write it, and that's how I'd recommend you write it. On your equation sheet, it looks like this. This is the College Board's way of saying, hey, you know what? This is a lovely equation. Remember, anytime you see these absolute values, that's the College Board saying, use this equation to find the magnitude, but not to find the direction. How do you find the direction? You draw an FPD. Okay. But remember, the reason I like to write it like this is because this is also equal to mg, which is gmm over r squared. Hey, look, my little m's cancel, so the acceleration due to gravity is equal to this. And in fact, if you were to plug in the mass of the Earth and the radius of the Earth, and then g, big G, which is on your formula sheet, one of the constants, 6.67 times 10 to the minus 11th, if you were to do that, you would actually get 9.8. And that's how you get 9.8. On the formula sheet, if you look on there, you will see this is on there. So G equals Fg over M. And they write it this way to tell you that, well, this should make sense because this is just, F equals ma just with G instead of a, but the direction, the magnitude of the acceleration due to gravity depends on the force of gravity and the mass. Okay, the direction of the acceleration due to gravity depends on the direction of the force of gravity. Duh. But remember, sometimes you'll see G as refers to as the acceleration due to gravity. Sometimes you're going to see it as the gravitational field. A lot of times with this one, it's you would write it in terms of meters per second squared. For this one, a lot of times you would see it as newtons per kilogram. But hey, guess what? Meter per second squared equals a newton per kilogram. It's the same stuff, okay? But just if you ever see it. So if they ask about gravitational field, it's asking you for little g. If they ask you acceleration due to gravity, that's asking you about little g. Okay, same difference. We did satellite problems with this, for example. Let's say you have the Earth, and then you have a satellite here, and this satellite is going to be orbiting around the Earth. And it asks you stuff. Well, what do? Well, you draw a picture. Typically in this unit, your picture is going to be your FPD. But hey, look, that's the only force acting, is force of gravity. And then you would write your equation. So you would say Fc equals the force of gravity, which is mv squared over r equals gmm over r squared. And if you look, you see how nice this is by writing it big M, little m? I just canceled out the mass of my satellite. So, and then I could also cancel out one of these r's, so I'd get v equals the square root of gm over r. You're not memorizing that, you're understanding how you got it, so you can solve it every time. But you could figure out, hey, at a certain altitude or a certain radius above the Earth, you could figure out how fast you would need to go. With that in mind, if the wording says at a certain altitude, that's where you have to be careful. So let's say you have a planet, it has a radius of r, and it says that you are at an altitude of 2r. Well then, for the equation here, if you're doing this one, this would have to be 3 times r, because you always measure from center to center. Okay. Other thing to keep in mind, if this was a spaceship, a really common misconception is people think, oh, well, there's no gravity, that's why they float around. No, they are floating around because there's no normal force. See, there is definitely gravity there. The only thing and they're just free falling around the Earth rather than free falling into the Earth. But so there's that. And then last In this unit, we talked about kind of the space stuff and this idea. So let's say I have the sun here. Okay. And if I have something orbiting the sun, really remember that orbit actually is an ellipse. Okay, it's an ellipse going around. So far, and again, as I progress with this, we can explain why does it look like an ellipse and what happens to the motion in terms of energy, in terms of angular momentum. But for right now, as it moves closer to the sun, it speeds up. As it moves farther away from the sun, it slows down. Let's talk about why that is. So, hey, look, here's a point. It is, let's say it's moving this way, so it's moving closer to the sun. If you look, my velocity points that way. The net force points that way, towards the sun. Well, if I break it into its components, hey, look, that guy is going to cause it to speed up. This one is going to cause it to change direction. If I was to do some point, any point where it's moving away, so let's do some point here where it's, hey, its velocity is going this way, and then my FG is pointing that way. Now the FG here would be bigger because it's a smaller radius. But if I was to break this into its components, do you see how this little guy is pointing the same direction, so it's causing it to speed up? This one right here is going to be causing it to change direction. This would be the centripetal force, and then this would be more the force causing it to speed up. If you remember, so, Kepler's three laws where things move in ellipses. When it goes closer, it speeds up. When it moves further away, it slows down. And then his third law, you might say, I want to memorize that. No, you don't. Okay, if I just draw an FBD, so I'll just draw, here's my FG. We're going to pretend it's moving in a circle. So I get FC equals FG. I get MV squared over R equals GMM over R squared. I'm going to do some algebra here. Goodbye M, goodbye M, goodbye R, goodbye R. Well, if it's moving in a circle, then this is true. We're going to pretend it's moving in a circle for this. Otherwise, we have to do calculus. So if I plug that in here, I get 4 pi squared R squared over T squared equals G M over R. And now I can cross multiply, and I get R cubed over T squared equals G M over 4 pi squared, which means everything, so I get this, which means everything in my system, for everything in my system orbiting around, this is going to be the same, which means everything in my system means that's going to be the same. All right. Bye, kids.